The subject of this lecture is motion. Here I will discuss the various quantities which are used to describe motion. I will also discuss the relationships between those quantities, and I will show you some example calculations to help you understand better how those quantities are used to describe motion. The first quantity that we will discuss is speed. Speed is measured on a speedometer, and it is simply defined as the distance traveled per unit time. Speed is measured in different units depending on the measurement system. For example, in the metric system, the most common units for measuring speed are meters per second or kilometers per hour. While in the imperial system, we have miles per hour or feet per second as the most common units for measuring speed. And so the units here show us that speed is calculated as the ratio of distance divided by time. We have units of length in the numerator, of these units. And then we have units of time in the denominator, of these units. And so this relationship would look like so. Speed is equal to distance traveled divided by the time to move that distance. Replacing those three quantities with their symbols, the formula that relates speed, distance, and time looks like so. The speed v is equal to the distance d divided by the time t. So again, v is speed, d is distance, t is time. So let's illustrate the concept of speed with the following example. A car traveled 100 kilometers in 2 hours. What was the speed of the car? So let's look at what we know from the statement of the problem. We know the distance that the car traveled. So the distance d is equal to 100 kilometers. And we also know the time of travel. So t is equal to 2 hours. What we're looking for is the speed of the car, v. Okay, so if we look at the formula that we have available on our formula sheet, we see that there is one formula that relates those three quantities, v, d, and t. And this formula is the formula that I discussed on the previous slide, and that is that v is equal to d divided by t. If you remember from the steps that I discussed about solving problems, I said that we find the formula that we will use, and then if necessary, we'll have to move things around in that formula to express the unknown quantity in terms of the known quantities, and then substitute the known values for those known quantities to calculate the result. In this case, this formula, the defining formula, already has the correct form for the calculation. So the speed v is expressed in terms of the distance of travel and the time of travel. So I just need to substitute d and t values in the formula and calculate the result. So replacing the distance d with what it's equal to, that is 100 kilometers, dividing by the time t, which is 2 hours, I get 100 divided by 2. And the units of the result will be the ratio of kilometers divided by hours. And so 100 divided by 2 is 50, and the units of speed are kilometers per hour, as discussed on the previous slide. So from the result here, we can make the following observation. Speed is just a number that tells us how fast an object is moving. However, speed does not tell us the direction of motion of this object. So when we say that we're driving with 60 miles per hour, that only tells somebody that the speed of motion is 60 miles per hour, but it doesn't tell that somebody in what direction the motion is happening. A quantity that tells the direction of motion as well as how fast the motion is happening is called velocity. Velocity is a quantity that describes the speed of a moving object and the direction of motion. contrast that with speed only, which is a quantity that only tells us how fast an object is moving. So to contrast the two, from the previous example, we calculated the speed of the moving car, and that was 50 kilometers per hour. So again, this just shows how fast the car was going. Now, if I wanted to talk about the velocity of the car, if I knew the direction in which it was going, then I would say that the car was going with 50 kilometers per hour. Let's say it was going north, due north. So now I'm giving the velocity of the car versus just the speed of the car, which is just how fast the car was going. And so quantities that are only numbers are known as scalar quantities, and quantities that are numbers and direction associated with them are known as vector quantities. And so in physics we have a large number of scalar quantities, but we also have a good number of vector quantities. And it turns out that for certain quantities, the direction is an important part of the explanation and describing a phenomenon which is related to those quantities. So let's define scalar quantities. Scalar quantities are quantities which are just numbers. And so there is multiple examples for scalar quantities. For example, time, speed, mass, volume, energy, temperature, pressure, voltage, so on and so forth. All of these quantities are quantities that only have a value associated with them but have no direction associated with them. We can't talk about mass in certain direction, or volume in certain direction, or energy, or temperature in certain direction, and so on and so forth. In contrast, vector quantities are quantities which are defined by a value and direction. And so examples of vector quantities that we will encounter in the course are velocity, acceleration, force, momentum, torque, and so on and so forth. So in discussing those quantities, the direction portion of the definition is extremely important to understand the nature of how those quantities determine how the phenomena in which those quantities are encountered work in the world. Now let's look at the following example. It takes a car 1.5 hours to get from town A to town B, and those two towns are 120 kilometers apart. The question is, what is the car's speed in units of meters per second? Okay, so let's see what we have given in this problem. So the information provided is that the time of travel was 1.5 hours and the distance of travel was 120 kilometers. And we are asked to find the speed, v, in meters per second. So from the information provided, it's clear that the units of distance and time are not going to, when substituted in the formula, will not give us the units of meters per second, which means that we will have to do a conversion of units. We'll have to convert kilometers to meters and hours to seconds in order to get the answer in the correct units. So the formula that I will use to calculate the result is the formula that I explained that relates speed, distance, and time. V is equal to d divided by t. I already have the formula in the correct form for my calculation, so all I need to do is replace the distance d with 120 kilometers and the time t with 1.5 hours. And so when I do the calculation, the result will have units of kilometers per hour, and then I will show you how to convert this unit into meters per second. So substituting the values for the distance and the time in the formula gives me 120 kilometers divided by 1.5 hours. That is equal to 80 kilometers per hour. So now I must convert those that unit, kilometers per hour, into meters per second. So in order to do that, let's remember that there is a relationship between kilometers and meters. And that relationship was that 1,000 meters are equal to 1 kilometer. Also, I can derive a relationship between hours and seconds. So 1 hour is equal to 3,600 seconds. So 1 hour has 60 minutes, each minute has 60 seconds, so 60 times 60 is 3,600. Okay, so now notice that my old units here are kilometers and hours, and kilometers are in the numerator and hours are in the denominator. So then I must create conversion factors from those two relationships that will ensure that I can cancel out the old units and end up only with the new units, which would be meters per second. So here is the conversion. So 80 kilometers per hour, I will multiply by two conversion factors at the same time. The first conversion factor converts from kilometers to meters. And so since kilometers are the old units and they are in the numerator, in the conversion factor I have the old units in the denominator, and the new units, which would be meters, are in the numerator. So 1,000 meters divided by 1 kilometer. Then the second conversion factor converts hours into seconds. Since the old units are hours and they are in the denominator, I have them in the conversion factor in the numerator, and the new units, which are seconds, will be in the denominator. And so the ratio here is 1 hour divided by 3,600 seconds. So now I can cancel the units of kilometers here and here, and the units of hours here and here. And what I have left is 80 times 1,000 divided by 3,600. And the units that this quantity will have will be what's left from the conversion, so meters divided by seconds. So meters per second. And so when you calculate this, you are going to get 22.2 meters per second, and that is the answer. Can this problem be done differently? Yes, it can. What you could do is first convert the 120 kilometers right here into meters, and the 1.5 hours into seconds, and then substitute in the formula for the calculation, and you will get the same result here. So either way works. I just wanted to show you the method to convert a unit that is not basic unit, that is a derived unit, into a different derived unit. The next quantity associated with motion is acceleration. So acceleration is the change in velocity per unit time. Or in other words, acceleration measures how quickly velocity changes with time. So if we want to put that in a formula type of relationship, we say that the acceleration is equal to the change in velocity divided by elapsed time. So what do we mean by change? Well, that would mean the difference between two values of the velocity divided by the time interval for that difference in velocities to occur. So we say that the change in velocity is equal to the final velocity value minus the initial velocity value divided by the time elapsed for the velocity to change from the initial velocity value to the final velocity value. Replacing the words in the definition here with symbols looks like so. The acceleration A is equal to the final velocity v sub f minus the initial velocity v sub I divided by the elapsed time t. So from here you can see how what the units for acceleration would be, and of course that would depend on the units of the velocity and time. So in the metric system, the most common unit for acceleration would be meters per second, also written as meters per second squared. And in the imperial system, the most common units are feet per second, or also written as feet per second squared. I'd like to one more time emphasize on the definition of change of some quantity, in this case change in velocity. So the change part in this term is labeled with the Greek symbol delta, which is a triangle. And so the change in velocity, delta v, is equal to the difference between two values of the velocity, a final value, v sub f, and initial value, v sub I. Similarly, I can calculate the change in any other quantity as long as I know two values of that quantity, and then I subtract what I would consider the final value, and what I would consider the initial value from what I would consider the final value. So we are going to encounter the term change in some quantity several more times during the course, and the same definition would apply. Now let's look at one example calculation which will illustrate how to calculate the acceleration of a moving object. So let's look at a car that is moving along a horizontal straight road. And so as the car is moving, when it is right here at this position, which I will call initial position, the car has velocity, which I measure, of 10 meters per second. And so since that velocity is measured at the initial position, I'm going to call that velocity the initial velocity. So the initial velocity of the car, v sub I, is equal to 10 meters per second. And of course the car is moving to the right. So the car is moving down the road, and at some point it reaches this new position, which I'm going to call final position. But now the car has different velocity, which I'm going to call v final, v sub f, and that final velocity is 20 meters per second. So the car started at the initial position from where I measured the velocity of the car at 10 meters per second and ended at its final position with velocity of 20 meters per second. And so then I also measured the time that it took the car to get from the initial position to the final position. And so that is the elapsed time, t, which would be equal to 5 seconds. Okay, so now I can use the definition of acceleration that I discussed on the previous page to calculate the acceleration of this moving car. So the definition of acceleration, the formula that defines acceleration, was that the acceleration is equal to the final velocity minus the initial velocity, and the result is divided by the elapsed time. So the final velocity is 20 meters per second minus the initial velocity, which is 10 meters per second, divided by the elapsed time, which is 5 seconds, gives us 10 meters per second divided by 5 seconds, which gives us 2 meters per second, and we can rewrite this as 2 meters per second squared. So that is the acceleration of the car as it's going down the road from left to right. So what is the meaning of this value? Well, it means that the car moves 2 meters per second faster every elapsed second. So if the car started at 10 meters per second, one second after that, the car will be moving with 12 meters per second. One more second after that, the car will be moving with 14 meters per second. And so on and so forth until the 5th second when the car is moving at 20 meters per second. So every second, the car speeds up by 2 meters per second. That's the meaning of acceleration. So this example is essentially the same thing as you driving a car and stepping on the gas pedal. You are providing acceleration in the direction of motion of your car, and as a result, the speed of your car increases from some initial value to some final value. Of course, we can also have the opposite process, meaning if you're driving with your car and you want to slow down, you're going to step on the brake pedal. And so as a result, your car will be slowing down and your final velocity will be less than your initial velocity. In this case, you're also moving with acceleration, but because you're slowing down, the term that's commonly used for acceleration in this process is deceleration. And so how do we indicate the difference between accelerating to speed up and decelerating or accelerating to slow down? Well, remember that when I discussed vector quantities, one of the examples was acceleration. So acceleration is a vector quantity, which means it has direction. So if a car is driving in some direction and it's speeding up, it means that the direction of the acceleration vector is the same as the direction of motion of the car. But if the car is slowing down, it means that the acceleration, which we now are going to call deceleration, is in direction opposite to the direction of motion of the car. So this directionality we can account for by applying a positive sign when the acceleration is in the direction of motion, and a negative sign in front of the value when the acceleration is opposing the direction of motion. Let's give an example. So here is a car which has initial velocity of 25 meters per second, and then after 4 seconds it has a different velocity, final velocity of 5 meters per second. So what is the acceleration of this car? Well, to calculate the acceleration, I'm going to use the same formula as before, and that is that the acceleration is equal to the final velocity minus initial velocity divided by the time. Now I'm going to replace the values for the two velocities and the time in this formula, and let's see what the result looks like. So we have 5 meters per second minus 25 meters per second divided by 4 seconds. So that is negative 20 meters per second divided by 4 seconds, or that is negative 5 meters per second squared. That's the acceleration. So what does the minus sign mean? It means that the car is slowing down because the acceleration is directed to opposite to the direction of motion of the car. So if I were to indicate that with an arrow, the acceleration opposes the direction of motion of the car. That's why the car is slowing down. If the acceleration was in the same direction as the direction of motion of the car, then the car would be speeding up. And so, to account for the direction of the acceleration, whether it opposes the direction of motion of the car or it's in the same direction, we use a sign in front of the value of the acceleration. So, when the acceleration is in the same direction as the motion of the car, the sign is positive. When the acceleration is in direction opposite to the direction of motion of the car, the sign is negative. So let's look at the following example. A car is moving or slowing down at a rate of negative 3 meters per second squared for 5 seconds. Find the car's final speed if originally the car was going at 30 meters per second. So let's identify what quantities are given and what we are looking for. Okay, so we know the time of motion, 5 seconds. We know the acceleration, which is negative 3 meters per second squared. How do we know that that's the acceleration? Well, from the units. So what I want to emphasize here, guys, is that you must remember the units that are commonly used for acceleration, velocity, and so on and so forth. Because when you read problems, understanding what the units for different quantities are tell you what these quantities are. So again, the acceleration is negative 3 meters per second squared. The initial velocity is 30 meters per second. Again, how do I know that that's velocity? But because of the units, meters per second. Those are the units for velocity. All right, and what I'm looking for is the final velocity. So, in order to solve this problem, I'm going to start with the defining formula that relates acceleration, initial final velocity, and time. So the formula that relates those quantities calculates the acceleration if I knew the final velocity, initial velocity, and time. However, here, the problem asks me to find the final velocity, this quantity right here. So, by the steps described in the previous chapter of how to solve a problem, first I'm going to rearrange the terms here to isolate v final alone on the right-hand side of this relationship. Everything else goes on the left-hand side, and then I'm going to substitute the values and calculate the answer. So the first step would be to deal with the denominator here. So since t is in the denominator, in order to remove it from the right-hand side and have it on the left-hand side, I'm going to multiply both sides by t. So we have a times t is equal to v final minus v initial divided by t times t. So t in the denominator here and the numerator here cancel out. And so what we are left with is a times t is equal to v final minus v initial. So now the next step would be to move v initial from the right-hand side to the left-hand side. So now I notice that v initial is being subtracted here. So therefore, if I add v initial on both sides, on the right-hand side, they will cancel out, and what I will be left with is just v final. So let's do that. So I add v initial to the both sides of this relationship right here. So we have at plus v initial is equal to v final minus v initial plus v initial. Minus v initial and plus v initial cancel out. And finally, my working formula now is that v final is equal to a times t plus v initial. Now I can substitute the values of a, t, and v initial here and calculate the result. So substituting the values, I have negative 3 meters per second squared times 5 seconds plus 30 meters per second. So here I have seconds to the second power in the denominator, and here I have times seconds, so the second power will cancel those seconds here. And so what I will be left with is meters per second only. So I have negative 15 meters per second plus 30 meters per second. That is 15 meters per second for the final velocity. And the units are correct. Those are units for velocity, meters per second. So my answer is correct. In general, in nature, motion happens with constantly changing acceleration. But describing motion when acceleration changes all the time is not straightforward at all. So in our course, we are going to limit our discussions only to motion which happens with constant acceleration. So such motion is known as uniformly accelerated motion, and a special case of that type of motion is free fall. So let's discuss the relationships that arise from the fact that the motion is happening with constant acceleration. So some examples of motion with constant acceleration. For example, a ball rolling downhill with no friction, a car increasing or decreasing its speed at a constant rate, or an object that's dropped from a building, which we know as a free fall, are examples of motion with constant acceleration. So we already discussed the relationship between the acceleration of a moving object and two values of its velocity and the time interval between those two values. So this relationship applies for motion with constant acceleration just fine. So let's write it down just to have it here for completeness. So the acceleration was equal to the final velocity minus the initial velocity divided by the elapsed time. But what about the distance traveled when the object is moving with constant acceleration? The distance traveled when an object is moving with constant acceleration d is equal to the initial velocity of motion of this object times the time of motion plus, and now we have an extra term right here, which is the product of the acceleration of motion, the time of motion to the second power divided by 2. Notice here that only the time is squared, not both the time and the acceleration, just the time, okay? And so this extra term here is the difference between an object that is not moving with acceleration, like the original formula that we discussed at the beginning of the lecture, versus the motion of an object which also moves with acceleration. So what you see from this formula is that if the object was moving without acceleration, this part was missing, the object will travel smaller distance compared to an object that's moving with acceleration, because this extra term here will add some more to that first term. So when an object is moving with acceleration for the same amount of time, it's going to travel a longer distance compared to an object that is moving without acceleration for that amount of time. To illustrate the calculation with the formula for distance traveled with constant acceleration, let's look at the following example. A train is slowing to a stop and it has acceleration of -3 meters per second squared. If its initial velocity was 30 meters per second, how far did the train travel in 4 seconds? So let's list the known and unknown quantities in this problem. So we know the time of slowing down, which is 4 seconds. We know the acceleration, which is -3 meters per second squared. We know the initial velocity, which is 30 meters per second. And what we're looking for is the distance that the train traveled within those 4 seconds. So we have the formula that calculates this distance. This is a motion with constant acceleration of -3 meters per second squared. So the formula for the distance traveled must include a term that has the acceleration. So on the previous slide, we discussed this formula, and the formula looks like so. D is equal to the initial velocity times time plus the acceleration times time to the second power divided by 2. So I don't need to do any rearranging of this formula because I'm looking for the distance, and the distance here is expressed in terms of everything else. All I need to do is just replace the quantities here to find the answer. So let's do that. So we have 30 meters per second times 4 seconds. So here the seconds in the denominator and numerator will cancel out. Plus -3 meters per second squared times 4 seconds to the second power. So the time here is the only quantity that's squared, that's lifted to the second power. And this is divided by 2. So the first term right here is equal to 120 meters. And then in the second term, I have -3 meters per second squared times 16 seconds squared. So 4 seconds to the second power is 16 seconds squared. So now I have the units of seconds squared in the denominator in this unit here, and the numerator in this unit here, so they cancel out. And so finally, I have 120 meters from the first term plus -24 meters. So this is -3 times 16 divided by 2. So that is 120 meters minus 24 meters, or this is 96 meters. So that is the distance that the train traveled. So notice that because the train was slowing down with this acceleration of -3 meters per second, it actually took the train smaller distance to slow down compared to if there was no acceleration. So if there was no acceleration, this term here would be missing, and so the distance traveled would be 120 meters. In the case of acceleration, when an object is speeding up, it's the opposite. The distance traveled is longer with acceleration compared to without acceleration. So now let's look at one more example in which we calculate the distance traveled with in a free fall motion. So free fall is a motion that happens with constant acceleration, and the acceleration of free fall we label with g, and that is equal to 9.8 meters per second squared in the metric system. This is also known as the acceleration of gravity or the acceleration due to gravity. So this is a constant value that you guys should know and remember and able to use for calculations when it's needed. So one more time, this is a constant value and it is 9.8 meters per second squared. Okay, so since now we have a specific acceleration to deal with in the case of free fall, I will rewrite the formula for distance traveled with constant acceleration to fit this case. And the formula is very straightforward. It is the same formula as for the previous discussion, motion with constant acceleration, except for now I replaced the general symbol for acceleration A with the more specific for this case symbol, which is G. And we again understand that G is equal to 9.8 meters per second. So the distance traveled is equal to the initial velocity times time of travel plus G times the time to the second power divided by 2. Let's look at the following example for free fall. Find the height of a building from which a ball was dropped if it took 4 seconds to hit the ground. So let's make a list of the quantities we know and the quantities we are looking for. So we know the time for the fall, that is 4 seconds. And we don't have any more numeric information provided in the problem. However, this is a problem about free fall. The ball was dropped from a building, which then means that I also know the acceleration of motion. The acceleration of motion is the acceleration due to gravity, G, and that is equal to 9.8 meters per second. And then I'm looking for the height of the building, the distance traveled by the ball from the release point. So we assume that the ball was dropped from the top of the building all the way to the ground. The formula that I will use for the calculation is the formula that I discussed on the previous page, and that is that the distance traveled in free fall is equal to the initial velocity times time of travel plus the gravitational acceleration G times the time to the second power divided by 2. So in this problem, I have no information about the initial velocity either. However, we read that the ball was dropped. It wasn't thrown, it was dropped, it was released from the building. So that implies that the initial velocity was 0 meters per second. So then that means that this first term here is equal to 0. So that actually simplifies our calculation because the distance traveled by the ball, which is the height of the building again, is just simply G times T to the second power divided by 2. And so that is equal to 9.8 meters per second squared times 4 seconds squared divided by 2. And that is equal to 78.4 meters. So that is the height from which the ball was released. So those concepts are the main concepts associated with describing how objects move. So acceleration, distance, time, velocity, speed, initial final velocity, all of those. Later on, we are going to discuss the reasons for motion of objects, why objects are moving the way they are moving, and that will introduce concepts such as force, mass, inertia, and we are going to talk about that in the next chapter.